Hi folks, Buckley here. Today we're going to talk about equations. So a few reminders before we get going. First is your formative assignments. So number 12 is due 2 p.m. on Monday, April 6th. Number 13 is due 2 p.m. Wednesday, April 8th, and will be related to what we're just about to cover. Prior reading from workshop number 12 was the chapter on illustration, so that's chapter 210 in the 4th edition, and maybe a slightly different number if you're in the 2nd or 3rd edition. Summative assignments. So congrats on getting in summative assignment number 1. The TAs and I are working on grading that, and we expect to have about a 10-day turnaround to get you your final grades on summative number 1. Summative number 2 will be posted later this week, and you'll be off to the races. We'll have the same type of process where you'll have a couple weeks to generate a draft, and that will be based on some content that we'll also be covering in class. And then you'll turn in that draft, we'll review it, and then we'll get you that feedback on your draft, and then you'll turn in your final draft after you make those revisions. Okay, another reminder, there is plenty of help live for the class. So the TAs are holding multiple office hours, and their information is on Canvas for how you can get in touch with them. I am also holding class discussions. They've been pretty fun. So every Monday and Wednesday, 3 to 3:30, it's fairly casual. We do discuss what we have just covered in that day's workshop, but there's also time to chat about some other things. So the link to that is on Canvas. Please join us for the class discussion. That is with me, Monday, Wednesday, 3 to 3:30. Okay, let's get going on our workshop for today. So our basic learning objectives for today are as follows. First, to recognize communication scenarios in which equations are needed and when they are basically superfluous. Second is to critique the use of equations presented in technical writing according to some established formatting standards that we will present. And the third is to use standard software. Specifically in this class, we'll be doing a lot with Microsoft Equation Editor to create and embed equations into written reports. There'll be a separate YouTube video on using Microsoft Equation Editor. It's not all that complicated, but there are a couple tricks I can show you on that as well. Okay, so let's get started with a self-reflection. So you have no doubt seen many equations in various engineering, science, or math textbooks over your many years in the education system. So I'd like you to reflect on what you've seen in various textbooks, and maybe you have a textbook handy. You could flip it open to just about any page. This is a physics textbook, college physics. And take a look at some equations. So flip open to a page where you see an equation. Here's one right here. And I want you to describe in your own words the situation in which the authors included that equation. Why was an equation actually needed in that instance? Examine the text adjacent to that equation and think about how the equation was situated in the text. How was it set up to present that equation? And then last, I'd like you to think about which formatting features that you have seen or that you're looking at in front of you related to equations. So how is that formatted presented in the text in terms of, that equation presented in the text in terms of formatting, okay? So take a minute and flip open any old textbook that you have close by and take a look at the way that the equations are presented there. Think about these 3 questions. Okay. Let's continue with this excerpt, and I'll point out a few things. So first off, there's obviously some equations, right? And this equation here is looking at, this is Newton's second law, so sum of the forces equals ma, and then rearranging that expression. Okay, so we have 2 instances here of equations being presented. Let's think about why an equation was needed. So if you were to think about how you could summarize that equation in words only. So you would have to say something like acceleration is equal to the sum of the forces divided by m, right? And in doing that, there's some klutzy language and there's also some detail that's missing. Okay, so while you could write out what I just said, the summation is a little, right, you could say summation, but it's better represented in a mathematical form. Note that I'm also having a hard time conveying the vector quality of the force and the acceleration when I'm saying that, right? So it's difficult to convey as text alone, especially summation and vector notation. We also don't have really nice words to convey division very cleanly, as opposed to things like addition, right, the sum of the following things, A, B, and C, or the product of to convey multiplication, division, and sometimes in some instances subtraction are a little klutzier to present in words, okay? Note that the text around this first equation and around the second equation as well describes all of the variables that are in that equation. So you have the total force, which is equal to the sum of the forces. This is presented. The total force on the object is the sum of these individual forces. The acceleration of an object with a mass of m is given by, right? And I would actually encourage this text to take one step further. They should have really presented also that a is the acceleration, but they're kind of setting that up, right? The way that things are presented graphically also matters. So those equations, when you are looking at this page, those equations really pop out on the screen, right? And they pop out because they're centered and they have extra line spacing around them, just like we do for a figure, right? They're also represented in standard mathematical typeface and symbolism. So you're seeing this equation as if you were seeing it with a professor perhaps writing it on the chalkboard in your math class, or me writing it out long form on a document camera, right? So it's presented as mathematical notation. Lastly, you'll notice that that first equation that we're talking about is actually numbered, and it's referred to later in that text, so equation 2.8. This one is not numbered. That's actually another little oversight of this text. Typically, every equation that matters, you're numbering it and then referencing it if you need to. We'll get to that in just a second. Okay, but you can tell that you've been reading a lot of equations already in these texts, and you're probably absorbing what already looks good in terms of an equation and what may look like it's off format or it's not completely presented in a clear way, because your textbooks are basically doing a pretty good job of presenting equations using standard conventions. So just taking a step back for a second, we've been working our way for a couple weeks now through each of the graphical elements. This is our last graphical element that we'll be talking about, which is equations. So equations are a graphical element. They're used to convey complex, theoretically based relationships between variables, right? So you're basically trying to summarize relationships between variables in a nice closed form way, right? The same formatting guidelines apply for all equations. So whether or not we're talking about a textbook, whether we're talking about an excerpt from an academic article, which is what you're seeing here, or a technical report like you guys will be writing in this class and others, you're using the same guidelines for equations. So you should see consistency everywhere an equation is presented to you in written text. So I've pulled here an excerpt from some work that I did a number of years ago. So this is a 2006 article by me. This is actually the article that came out of my master's thesis. So here's an equation, right, that's important in this article. This is actually the one equation that is presented as embedded in the text in the article. I'll show you a couple other equations that were used in a second. But you'll notice the equation is presented. It's neatly spaced. The text around the equation explains all of the variables. So the results of a linear finite element analysis were superimposed to correspond to an axial forcing function of the form, and then this is that function, right, where Fk, Xy are the force distributions, Sk are the arbitrary shape constants, blah, 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 blah. Okay, so the text around it is basically situating or presenting that equation and explaining all of the variables. The equation is centered with extra spacing. It's in standard mathematical typeface and symbolism. And then it's numbered for future reference if we need to do that. So again, you're seeing those same standards that you're used to seeing in a textbook. You'll also see them in academic articles and technical reports. So let's get into the formatting guidelines. What is important when we're examining and critiquing work of others related to equations, and then when we are creating our own equations that we want to embed into text. So when used in technical communication, equation must meet several general formatting guidelines. The first is the equation has to be necessary. It has to be non-obvious to the audience that you're talking to. So sometimes equations are obvious to some groups, but not obvious to others, so it's important to recognize your audience. And equations should be used when text cannot convey the information necessary alone, when the text becomes cumbersome to convey it. So equations should be embedded within the sentence structure of your report, And all variables within the equation should be explained in the adjacent text. So you don't want to be searching all over the text to figure out what a particular variable means. You want to look at the equation, and then I should be able to look at the text immediately adjacent to it and understand what is going into that equation. So you'll notice an asterisk there. I'll get into this in a few slides, but some deviation is permitted in special circumstances regarding embedding equations directly into the text, and we'll talk about that in a few. Okay, equations should be presented on a separate line. They should be centered and numbered. And there's a couple other details related to that we'll get to further. But centered and numbered so that they basically stand out from the rest of the text. There should be the numbering corresponds to perhaps an in-text reference that you would use later. So not all equations will be referred to in the text after you present them, but you do, when you want to refer back to that equation, you will refer to it by its equation number. Again, more on that to come. Lastly, equations are presented in mathematical typeface and symbolism, preferably using an equation editor. We can actually tell if you are not using an equation editor. So you will get your first experience with an equation editor later in this workshop. So let's start with general guideline number 1, that equations need to be necessary, non-obvious to the audience, and cannot be communicated by text alone. So here's an example from the 2019 Senior Design Team Tree Hugger. So we've been using this case study quite a lot. So this is a system that holds a small sapling in place. The tree hugger goes on top of the root ball and prevents the tree from blowing over in the wind as it's growing. So it was very important on this senior design project that the team understand the forces that would be acting on this tree under certain wind force conditions, right? So here's the equation that they wound up using. The net force on the tree canopy caused by the wind, VF, okay, so that's the force value, or I'm sorry, FV, F sub V, was determined using the expression, and then here's the expression. F sub V equals 1/2 rho air, V squared, A, C, D, where rho air is the density of air, and the values presented. V is the wind speed, okay, and we're saying that it's 150 feet per second under worst case conditions. Note the reference here. So if you're presenting a value here that is non-standard or non-obvious, let's say, that you had to look up, you want to present that reference. A is the projected area of the tree canopy, which is taken to be 15 square feet, okay, another reference, and CD is the drag coefficient, which is 0.5, okay, to reflect the porosity of the canopy. Okay, so again, this type of equation, right, this is something that would be non-obvious, right? It's not like saying, oh, let's take the average of this, let's take the sum of this. So you definitely want to present the equation in full. It would be difficult to communicate this equation by text alone, right? So describing this as the product of these three things with velocity squared is going to be cumbersome to describe by text alone. So that's a good example of a necessary equation to incorporate. Okay, so a little bit more on this. I've restructured this example just to show you something else, which is sometimes you want to manipulate an equation, right? So this is the standard form of the equation. And let's say that I am interested in back solving for the velocity, right? The maximum velocity that could be sustained if I know that FV was 150 pounds. So again, I'm kind of fooling with this example a little bit. One thing to note is that this equation here, so what I'm doing here is I'm basically back solving this expression for v squared, and I'd like to tell the reader that I do not need to show every algebraic step in order to do that. So equation 2 here really could go away, and really all you're talking about is presenting equation 3. So equation 2 in this instance would be superfluous, right? So you really don't need to show all of your steps like you would in a proof when you're doing a written document. You could start with, you can skip over some algebraic steps essentially. Okay, so that's something important to remember. All right, let's give an example now, a different scenario of a situation where perhaps there are equations included that aren't needed, that are not needed. Okay, so I wrote up a little text here. Compression tests were performed on washers from Melissa and Doug construction set in a box. Tests were conducted at failure at a rate of 1 millimeter per minute on a mechanical test frame. 20 trials were conducted, and the average failure load across all trials, F average, was determined as, and then I present this equation. And if you look at this equation, right, this is this is basically how to calculate the average across 20 trials. Okay, and then this is how to calculate the standard deviation across 20 trials. That's not really necessary to include, right? Average and standard deviation are basically standard measures, and that's something that a general audience, especially an audience with some technical know-how, which is who you're assuming is reading this, would know, right? So you could basically say 20 trials were conducted and the mean and standard deviation across all trials was determined. You don't need to present standard equations like average or mean and standard deviation, right? And there's a couple other examples of that as we move into things, but basically I don't need to see expressions for very common things like average and standard deviation, okay? All right, so moving on to guideline number 2. This is all about embedding the equation, okay? So the equation is embedded within the sentence structure and all variables are stated in the adjacent text, okay? So the way to think of an equation presented in this way is to really think of it as a word, so a single word in a sentence. So the net force on the tree canopy caused by the wind, F sub V, can be expressed as blankety blank, where rho air is the density of air, V is the wind speed, blah, 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 blah. So notice how that expression reads through the equation, can be expressed as blankety blank, where rho air, right? So I'm moving through the expression, and there's subtle things that actually show you this, right? So first off, you notice there's no additional punctuation here. Sometimes people will put a colon, and I'll accept that. But basically, it's as if you're just skipping down and reading through this, and then you're picking the sentence back up here. So this is an important point. This should not be capitalized. Microsoft Word will want to autocorrect that to be capitalized, but basically it's reading through this sentence, okay? So that's a complete embedding of the equation. All right, so there again, looking at what's adjacent to the equation to show that it's embedded. The other part here is that every single variable that's in that expression is explained in text. Okay, so F sub V, rho air, V, A, and CD are all explained. So I don't have to go hunting for what each of these variables are going to mean. Okay, all right. So I do want to talk now about the one deviation. So there are instances in which you just have so many equations and so many variables that it gets really cumbersome to lay those all out in embedded text. Meaning if you were to describe, let's say, 20 variables that you have in your equation, that paragraph would be really, really cumbersome to read. Okay, so what you do in those instances, and I'm going to use this model again from my master's thesis, is basically you create some sort of a table. Okay, so this is the math that goes behind this. This was the one equation that was presented as embedded in the text, and then this was a table that came later that basically showed all of the functionality that goes beneath that, right? So you've got yourself, here are each of the variables that I'm explaining what they are, okay, and then here are the sub-equations that kind of relay off of each other that are being explained. Okay, so this level of detail isn't something that you'll see a whole lot. Maybe by the time you're a senior, there may be an instance in a senior design report or in some 300 level classes where it would be better to present some of these interrelated equations and variables in table form rather than in embedded text. But for the most part right now, you guys are going to be dealing with embedded text. But I just wanted to let you know where it would be acceptable to kind of deviate from that and convey the information in table form. Okay, moving on. Guideline number 3. So equations should be presented on a separate line. The equation itself needs to be centered, and it needs to be numbered, and these numbers are sequential. So throughout the main report, I should see equation 1, 2, 3, 4, 5, blah, 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 all the way through. When you go to the appendix, you tend to put the appendix number in front of it. So if this were appendix A, it would be A.1, A.2, okay? The numbering needs to be right justified or as close to right justified as you can get. This allows you to scan, the reader to scan down the page and see exactly where those equations are. So this, you can think of this almost as the figure number, right? But it's an equation number. And again, these numbers restart. Okay, so you wouldn't have like figure 1, equation 2, right? So you restart it. It's a fresh set of numbers for the equations. Okay. Last point is the in-text reference. Okay, well, actually I want to show you this. So notice that the spacing and centering really highlights each equation. And then the numbering, if you were to refer to that equation later in the text, so the corresponding wind speed can thus be determined by manipulating equation 1 as you're just referring to this equation just like this. I don't need parentheses, I don't need anything else, right? Equation 1, make sure that is capitalized. That's the proper way to do it. Okay. All right, I do want to show you what the formatting looked like originally on this report, and this is no shade thrown at the authors of the original report from Senior Design, but their formatting was a bit off. So this is actually how they presented, in an appendix, they presented the entire calculation related to force of the wind, okay? And you'll notice that the way they're presenting this, which is 2 columns of just sort of solid line by line, stepping through their calculations, and it's doing a couple things. I mean, the first thing that's kind of, I give them props for defining each of their variables, that's good. But they haven't well separated out which is a variable and which is an equation, right? And which is a constant that's being provided. So it's kind of mixed. All of this means that the really important equation, which is this guy here, is kind of lost in all of this, right? So if I'm reading through the report, I want to see what your most important equation is right off the bat. And I have to kind of hunt to find this in all of these statements that they're just kind of laying out. So again, this would be a much better way to present it, where each of the values that you're showing here is given one by one and there are proper references, okay? All right, so general guideline number 4, our final guideline, is that the equation should be presented in mathematical typeface and using mathematical symbolism, preferably done using an equation editor. Okay, the mathematical symbolism that's used here in this expression that we've been working with is not all that complicated, right? There's a symbol here, a Greek symbol, rho for density. There's a square here, which could be done in Microsoft Word just using regular typeface by using a superscript. We've got a subscript here on C. We've got a half symbol. But this was done in an equation editor, and you can kind of tell, right? You can tell if I compare versus what the original report had. This original report, it's very obvious to me at least that this was done in Microsoft Word directly and not using an equation editor. So there are a couple things that give that away. The first is that this half symbol, right, that fraction, this is notation that you would get if you were just typing out on your regular keyboard here using Microsoft Word. This is what you would get if you format using an equation editor. Rho here, this is non-standard typeface, mathematical typeface. This is the standard mathematical typeface. Okay, the superscript and subscript looked okay, but then you've got these weird asterisks here, which is sort of a coding, right? So if you think back to CISC 106, you use asterisks and caret symbols to do multiplication and taking superscripts, right? So here we've got a format here, if you're using an equation editor, that's concise and readable. So this looks exactly like what you'd see in a math class or a theory-based class. It's standard mathematical representation, particularly for things like the fraction. It's a consistent typeface, so all this type looks like each other. This does not, right? There's no coding notation, so the asterisk or the exponential, okay? All right, and over here we've got a less concise and less readable layout. Notice how much more room this takes up. Non-standard mathematical representation, inconsistencies in typeface, and it's got some coding notation here, like this asterisk here, when in reality the way that we would represent this in a math class is to just abut these variables, right? Excuse me. Okay. So going through all of this, these are the minimum necessary requirements for guidelines for equations. And I've summarized them here in a detailed formatting guideline for equations. It's just one page. Necessity, embedded, in-text formatting, and equation formatting is what you're looking for. Now it's time for our class participation activity. Everybody's going to be working with the same document. Please use subsection. You're going to go to the green case study, go to Appendix E of the green case study, and look at subsection E2 only. There's an E1 and an E2. I want you just to focus on E2. You're going to go through and review the equations used in E2 according to the formatting guidelines document. And just a little bit of context before you start. What this section has to deal with is these are the guts of the cervical dislocation model. Again, this is to euthanize chickens, poultry. Okay, this is a trainer that the group made in senior design to train techs how to euthanize poultry humanely by performing a cervical dislocation, so breaking its neck. This is the surrogate chicken neck, okay, and it consists of a ball and a socket. The equations that you're looking at are the math to determine the fit, okay, the geometric parameters for that socket that would allow the ball to pop out at a certain force. Okay, so the team did a beautiful job of finding a reference for that and really working with those equations to not just guess at their design, but to really design it. Okay, so with that context, I want to set you loose. Please put me on pause. Tackle the green case study, Appendix E, subsection E2. Look at all of the equations there and review them all at once. So again, with this formatting guidelines, you don't have to go equation by equation, just look at all of the equations together. And the note down at the bottom basically says, you can specify which equation may need improvement, but you're going to do the review for the entire subsection at once. Okay, put me on pause, take care of your class participation activity, should take about 15 minutes, and then restart me and we'll talk about it. Okay, let's just discuss kind of high level some of the things that we could see in that class participation activity. So again, we're talking about the green case study on the cervical dislocation trainer. The team was looking to calculate what the snap fit should be between the ball and socket to get the kind of dislocation force that they were looking to mimic. And they've got a set of equations here, all right? And first thing that I'd like to call out is that it's obvious that these equations are non-obvious equations, right? So this is not an instance where you could describe this well with text. Try writing out that expression in words. That would be very, very difficult to convey. So the equations are definitely needed. But the way that they're presented, if we look at the embedding, simply stating the questions really isn't embedding, right? All equations were found from, and then this is a reference that they used, okay? So I should see a reference number here, and that's not there. But just saying, here are all of the equations really isn't doing a great job of embedding, okay? So it also is problematic in the bigger sense that it doesn't convey which of these equations is the most important or the driving equation in this presentation. So that driving equation is actually force. What is the force to cause the dislocation? And computing P and K are actually sub-equations to get at these various parameters, right? So K there determines P. P is an essential input to this equation for F. So those should really be presented as three separate equations where you're explaining the variables in between each. This table down here is interesting, okay, but this is something where you may not need to embed or recreate the table directly. So it's basically talking about what this parameter is here. And for different retaining angles that the team may choose to use. They could basically have just cited this source. So instead of pulling that table, taking a screenshot of the table from the original source, they could have actually just cited that source and be on their day, okay? But basically some of the other things are good, so they did go about explaining what each of these variables means. This is a lot of information all in a row, and they're not giving their input values for it, so it probably would have been better. This may be an instance where a table would have been a good addition, okay? But they did state them clearly. Additionally, if we look at the formatting itself, this is non-standard line formatting. It needs to be centered, so the equation should still be centered, and the number needs to be right justified, okay? And this is Appendix E, so I would expect to see an E prefix before that. In terms of the formatting for the equations themselves, they obviously did use an equation editor, so getting this kind of embedding here, you can't do that in Microsoft Word just on a regular type line. So they are using the equation editor, but they're still using some symbolism that's kind of coding symbolism. So with a couple tweaks to their formatting, they may be able to eliminate all of that coding formatting and compress the length of those equations as well. Okay, so those are most of the essential edits that I found, at least. Hopefully you found a couple others and are making suggestions on ways they could improve the presentation of equations. Okay, I want to switch gears ever so slightly here as we're wrapping up this workshop and talk about how to create equations. So creating equations is best done with an equation editor, some sort of software package that allows you to create these equations as basically image files. So there are some great packages that are out there. The two professional grade packages are LaTeX and MathType, and you are welcome to use those. The easier of the two to use is actually MathType. But I would strongly recommend actually equation editor in the Microsoft Word or the Microsoft Office suite has gotten much better. So this is the little symbol for equation editor. But Microsoft Word and PowerPoint, and actually Excel if you wanted to do that, but Word and PowerPoint are the most common. There is a tool, so if you go to Insert and then Equation, it actually brings up a little app that was a third-party app that Microsoft adopted that is actually much better than it used to be. So we will be exclusively working in Microsoft Editor, and I'll have a separate tutorial for you on how to work with it. It's fairly easy to do, but all of these packages have preset mathematical typeface and symbolism, so you can get integral signs, you can get derivatives, you can get fractions of any kind, you can get summations. The equations that are being generated can be repeatedly edited, copied, and pasted into text. This is particularly true if you're using the Microsoft Editor, equation editor app. So it is designed to work really well with Microsoft Word or PowerPoint, which means you can just very simply click on it and start your editing. You can move it around like you would an embedded image in the text. It embeds directly into the documents and to the presentation. So we'll be working with Microsoft Equation Editor exclusively, but just know that there are several other types that are out there, MathType and LaTeX being the most common. Okay. So this brings us to our formative assignment. So formative assignment number 13 involves you creating a document with multiple embedded equations. I am basically, there's going to be a YouTube video of me going through on a document camera the equations that are involved in determining how far a rubber band will fly horizontally, right, through the air after you stretch it. So if you do something like this at home, you grab a rubber band, you pull it back over your finger and you stretch it a certain distance, then you shoot it horizontally, how far is that going to travel? Okay, so we've got projectile motion, we've got plenty of conservation of energy, so there'll be a lot of equations involved and you have to explain those equations as you're working through it. Okay, so formative assignment number 13 will explain everything that you need to do, but basically you are going to be creating a document based on the information that I'm presenting in handwritten form. You're going to create a document in Microsoft Word that has embedded equations that is explaining the math behind this physical phenomenon. I assure you that this assignment that you're doing is not wasted effort. You actually are going to wind up using what you have written in your summative assignment number 2. Okay, so that's a little sneak peek, a little hint at what we're going to do in summative assignment number 2. Okay, so that's your formative from today. Again, there will be 2 YouTube videos posted. The first one is 2 additional YouTube videos posted. One is of me just working in Microsoft Equation Editor to give you a feel for that, and the other will be related to formative assignment number 13, where I'm basically going through and solving by hand or presenting by hand the equations that would be involved in this phenomenon. Okay, so this is wrapping things up. Again, formative number 12 is due 2 p.m. Monday, April 6th. Formative number 13, which is you creating the rubber band shooter math, is due 2 p.m. on Wednesday, April 8th. Required reading is the chapter on equations, which in the 4th edition is chapter 211. If you have a different edition, you can hunt around a little bit. Summative assignment, we're working on a 10-day turnaround for you, so we should have those grades posted. And a summative number 2 will be posted by the end of this week. Hope to see many of you in our discussion Monday, Wednesday, 3 to 3:30. Link is on Canvas, and please use the TAs if you have any further questions. All right, guys, thank you.